Hello and welcome to this video. A special welcome to those who are new to the channel. Make sure you subscribe to the channel and press the bell icon so that you can get notification about upcoming videos and data structures and algorithms. And once we finish the data structures implementation, we will solve problems for coding interviews because data structure is quite popular topic in all good companies, and they ask questions which resemble something like competitive programming. So without further ado, let's get started. So my earlier videos was on graph, and I was doing shortest path algorithm. We implemented adjacency matrix based shortest path, but for adjacency list based shortest path algorithm, we need a priority queue, which is implemented through a heap. So I thought that I will make a video on heap because I have not covered heap. So heaps are of two types. One is min heap, another is max heap. So a heap is a complete binary tree that satisfies the heap property. So what is the heap property is that in the case of a max heap, the root node will be the largest, and the subtrees will also have this property. So 20 is the largest in entire left tree, that is this side of the image, max heap, and 18 and 16 are its children. 18 is greater than its children and 16 is greater than its children. The same property is satisfied in a min heap also, but in this case smallest is at the top, and subtrees also follow this property. So let's look at the properties of a heap, and I will go through this list. A heap is a complete binary tree. This implies that all levels are fully filled except last level, that is leaf nodes exist only at the last level. The largest or the smallest value is always at the top, as we have seen. Parent and child have a special relationship. If index of, this should be of, parent is I, then children are at index 2i plus 1 and 2i plus 2 for zero based indexing. So let's look at this relationship a bit. So suppose 20 is 0th element, then 18 is 2i plus 1, that is 2 into 0 plus 1, that is first index. 16 is at 2i plus 2, that is second index. Now 15 is 2i plus 1, that is 2 into 1 plus 1 at third index, 0, 1, 2, 3. Then this will be at fourth, that is 2i plus 2, 2 into 1 plus 2, that is 4. This is at fifth index, this is at second index, so this is at 2 into 2 plus I, and so on. That follows naturally from the complete binary tree property. Now insertion and removal are efficient and have a time complexity of O log n. Because the binary tree is complete, the complexity does not worsen more than log n. Insertion and deletion both will happen in time complexity log n. Efficient access to the largest or smallest element with a time complexity of O1. Since the smallest or largest element is at the top, we can get it very quickly in constant time, and that is why heaps are good for implementing priority queue. We don't care about traversing the entire element in the heap. The only thing we care about is the root node. We normally do not perform traversal in a heap. Now we look at the insertion of a heap. So suppose this is the initial state of heap where 20 is at root node, 18, 16 are children, 15, 17 are children. The new element will be inserted at bottom rightmost leaf node as a bottom rightmost leaf. So 25 will be inserted here, but this violates the property of max heap because 25 is greater than 16. So 25 and 16 will be swapped like as shown here. Now 25 will be less than 20, so it will be swapped again. So this is the final state of heap. Similarly for deletion, the bottom rightmost element is copied with root node. So 17 will go at top. Okay. And then 20 will be deleted and 17 and 18 will be compared and 17 will be brought down to left side, or you can bring it to the right side. So both will be valid in this case. So the property of pushing elements up and down is called heap up or heap down. That is the typical name of the function. This process is called heapifying process. So with this out of the way, the algorithm, let's look at the implementation. So as always, I have three files: main.c, which is this should be max, and this is max. Okay, max heap.h. Why can't it find it? Okay, now it is gone. For a moment, the CPP tools was underlining it red. So I have this main.c file, which is the driver of the program. I create the heap and push values, and then we look at the top and we pop the head, and we look at top again. Now header file is, so a since it's a complete binary tree, it fits on an array or a pointer very nicely. So we have used a pointer to store the values, and the type of values which will store are integers. We have a size which will determine the size of this pointer p. We have a count which will count number of elements in the heap. We have create heap function, heap up, heap down, push, pop, top, and size. Size is not useful. We can delete it because size we can always invoke size element. There is no need of this function call. Let's look if somebody has called size. No, nobody has called size, so let's remove this. Okay, so now we go and look at create heap function. So heap allocates the size of heap. We set size to 1. We allocate for size number of elements in memory, count is set to 0, and we return this heap pointer. Now the first operation in main is push. So the two functions are called push and pop. We look at both of them. So we start with push. So I have written here initially count is 0, size is 0, we have no elements in the heap, and we have space for one element, that is 10, not 10, make it empty. So initially we look at whether count is greater than size or not. So count is not greater than size, we don't return. Now we allocate at the root, because count is 0, the value x. Suppose the value x was 10, so we insert 10 here. Now count is increased, we increase the count. Now we see whether 4 into heap count, that is 4 into 1, is greater than size was 1, greater than 3 into heap size. So 4 is greater than 1, so we double the size of heap. So now there will be an empty space by relocation, and then we call heap up with head heap and heap count minus 1. So what it will receive is the root node and index. Index will be 0 in this case, so 0 minus 1 will be 2, that is a negative value, minus half, which is not less than 0. Minus 1 by 2 would be 0 or minus 2, depending on minus 1 which way it rounds. Okay, I don't recall which way it will round. Most probably it will be rounding towards nearest integer. In any case, it is not less than 0, it will return. So it will return, and this is the current state of heap. Now suppose we push another node 12. Okay, so at this moment size is 2. So heap count is not greater than heap size. Okay, so at heap p plus heap count at x, we allocate 12. Okay, in the tree form it will look like, in the tree form 10 will be at root node, and then it will look like this. 12. So 10 is at the root, 12 is here. Now this violates the heap property, okay, but that will be fixed as you see this. So count is increased, now count becomes 2. Now 4 into 2 is greater than equal to 3, greater than 3 into 2. So size will be doubled again, it will be 4, and reallocation will happen. So we will have 2 more empty spaces here. This reallocation makes this efficient to manage the size. Now it will call heap up. Now heap count is 2, so it will receive 1 here as index. 1 minus 1 is 0, 0 by 2 is 0, which is not less than 0. So it will go here, it will check heap p plus index. So index is this and parent is this. because parent is 0. It will see that this value is greater than 10. So it will swap. This is basically a swap. Okay. So 12 will come here and 10 will come here. Now parent is 0. So 0 is sent, and it will see that 0 minus 1 less than 0 minus 1 by 2 is less than 0. So it will return here. So our max heap property is satisfied. Suppose we enter another element. Let's say we enter 5. Not 5. Let's destroy the heap property. We enter 15. So similarly, it will check at whether heap count is greater than size or not, which is true. So 15 will be put in here. Okay. Now head count grows, heap count grows 3. Now 3 into 4 is 12, and size is 3 into 4. So no allocation will happen. It won't reallocate. It will send it here. So count at this moment is 3 and size is 4. So it will receive 3. 3 minus 1 by 2 is not less than 0. And it will see here if this value is greater than parent. So it is greater, it will swap. Okay. Now no parent will become what? Parent would be 3 minus 2 minus 1 by 2, that is 1 by 2, that is 0. So 0 will go and no further changes will happen. So this is how we maintain the max heap property of a node. If for example we can insert another node, let's insert, so 15 will go at here in the swap. 15 will go here. This will be 10 and this will be 12 in the swap. That is what will happen. Okay. And we can easily verify this. Now let's insert one more element. Let's say we destroy the heap property again. Let's say we insert now the tree. In the tree form, it will look like this: 10, and this will be 15. 10 and 12. This is how it will look like. Okay. Now we look at this is red because there is space, no space, so that will continuation. Now we destroy the heap property again. We insert 18. So now 18 will be allocated in the beginning as we follow this logic here. Okay, I will have to insert a new line here. This will look like this. Okay, at this moment count will become 4 and size is 4, so reallocation will happen, and 8, size will be 8, so 4 more spaces and 18 will be here. Okay, now okay, we'll see, there is something wrong going on here. Declaration is incompatible with void heap. Okay, I don't think there is problem here. We look at this, we will fix the program later. We look at 18 here. So the count size is now 4, size is 8, so head count will be 3. So 3 minus 1 by 2, that is parent would be 3 minus 1 by 2 will be 1. So parent is 1. 1 is this node. So obviously it will swap. So it will become 18 and it will become 10. And then parent is 1. It will go again. 1 minus 1, that is 0 by 2 is 0. So 0 is not less than 0. Swap will happen again. And 15 and 18 would be swapped. So finally it will look like 18, 15, 12, 10. So this is how the heap will continue to build. So I hope this example makes how the insertion happens. So oh, there's a brace here. Okay, this is causing the trouble, backslash. Okay, so this is how push and heap up will happen. Now we look at pop. Pop is slightly more involving, but let's go through this. So suppose this is our heap and we pop. Okay, so heap count is not 0, so heap count is 3 now. So let's write it here. Heap count becomes 3. Temporary is heap plus heap count. So temporary would be 10, and it will be swapped with the count and p. Okay, so 10 would be swapped with 18 over here. This is a swap, so it becomes 10 and this becomes 18. We do not necessarily remove this. Now it is checked whether 4 into heap count, 4 3 are 12, is less than heap size or not. This is just memory allocation routine. So the element is not necessarily deleted from the heap in this program. We just make sure that our root node is the largest. Okay. The reallocation will happen when there are lots of elements which are actually popped from the element, and count has become very low. Then the reallocation will happen and the elements will get removed from the code. So now we look at our heap down function. So our current status of the heap is there will be syntax errors, but okay. Our current status, the heap looks like 18 was here, 10, oh, swap has happened, 10 15 12 18, 10 15 10 15 12 18. This is how our heap is looking right now. Okay, so the index which we received was in pop, index which we received was 0. Okay, so at 0 10 is there. So we look at left is index into 2 plus 1, that is 15. Left and right is 2 plus 0 plus 2. So now we look at left is less than equal to heap count or not. Our heap count is heap, let's write it on this line to avoid the syntax error. Count is equal to 3. Count was 3. Okay, so for maximum it took heap p plus index was 0, so maximum is 10. Maximum is 10. Okay, now it compares whether left is less than heap count or not. So left is 1, heap count is 3, so left is definitely less than heap count, and maximum is less than heap p plus left, so 10 is less than 15. So it will put 15 as maximum and left flag 1. Left flag 1. Now it will see if right is less than heap count or not. It will see it is less than heap count and maximum is less than right or not. So maximum is 15, is not less than 12. So it won't enter this one. Now left flag is 1, so it will enter here, and left and index will be swapped. Okay, and index would be made maximum. So this would become 15 and the left node will become 10. Okay, now it will call with the right value. Now it will call with left value. So left value was 1. So now index is 1. So once index is 1, it looks at left. So left is 18. Okay, so this would become 1 into 2 plus 1, so 3. Now maximum would be 18 now, and following the same logic 18 and 10 would be swapped. Hang on, 10 and 18. Yep, it would be swapped. No, count is 3. So left is not less than heap count. It won't enter here. Left is not less than heap count. It is 3. So it will look at right, but maximum is not less than heap p plus right. 18 is not less than 12, so it will not enter either of these and will return. And then that means now element 18 is removed because of the relocation. It is not actual deletion, just that count is maintained till 3. So count is 3 means these many elements are considered 15, 10 and 12. And once suppose this heap grows and there are lots of such elements which are not actually in the heap, the relocation will make sure that they get deleted. So this is the entire logic of how the heap is implemented. The top is very simple. You simply return head p, and if it is empty then you return int min. Empty checks whether heap count is 0 or not. So we have implemented our max heap. Let's compile this and see this in action. So initially 10 was at the top, then pop top was asked, then we put in 18 and 13, so 18 would be at top. The top element is 18. Then after popping 18 we will have 13. After that popping will be giving us 10. So this is how max heap is implemented, and I think I have explained it in very simple manner. So with this I will end this video here. I hope you have found this video useful and informative, and please like the video, share as much as you want on social media, make use of the comment box. I would like to interact with you guys. You may be a veteran programmer or you may be a new programmer. New programmer does not matter because you might be a lot more intelligent than I am. So please interact with me in videos and let me know what other videos on data structure and algorithms you want to see, and I'll try to make those. Thanks a lot for watching. Happy programming.